All right, we're moving on to our next session featuring Ben Butler Cole from Neo4j. Please don't hesitate to ask questions using the Questions tab on your screen. We'll have a brief Q&A session at the end of the presentation. And now here's Lance Walter.
All right, well, I probably don't have to tell this audience that a big reason that a lot of organizations are choosing the cloud is because it makes so many things easier. We hear from user after user that they want to spend more time working with applications, more time working with their data, less time on operations, less time on infrastructure. Well, making it as easy as possible for you, our customers, turns out to be pretty hard work. It takes a lot of effort behind the scenes. And Ben Butler Cole from our product team is going to tell you more about that as we look under the hood with Neo4j Aura. Ben Butler Cole's been with Neo4j for more than 7 years now and has led many of the architectural conversations and decisions for Neo4j Aura. Prior to Neo4j, Ben worked for nearly a decade as a programmer for ThoughtWorks, a leading consulting firm focused on software development. So let's learn more about Aura under the hood. Welcome, Ben.
Thank you, Lance. I'm Ben Butler Cole, architect on the Aura team at Neo4j. In this talk, I'm going to lift the hood on Neo4j Aura and show you something of what's under there. In particular, I'm going to talk about 3 of the best decisions we've made while building Neo4j Aura, decisions that shaped how we delivered the system and how we designed it. First, let me give you a very high-level overview of the Aura architecture. The 2 components of Aura that our customers see are the console, our customer-facing user interface, and the Neo4j databases that we run on their behalf. Aura runs on the public cloud, specifically on Google Cloud. And recently, as we've announced, an early access program is available for running AWS-based Aura enterprise instances. And in the future, we plan to extend support to Azure as well. We use Kubernetes for orchestration in Aura. As I'll discuss later, we have 2 separate Kubernetes clusters in the system, one of which we call the brain, which runs the console, and the other which we call the orchestra, which runs the databases. There are also a number of control plane components running in each type of cluster. Our customers interact directly with the console, and the applications that they write talk to the databases. This brings me to the first of the decisions that I want to talk about. We put Aura into production before we wrote a single line of code. Although this is how Aura looks today, when we first built it, as you might imagine, it was a lot simpler. Pretty much the first thing we did once we got the go-ahead for a project to build a database as a service was to grab a couple of EC2 instances, install Neo4j on each of them by hand, and then tell people inside Neo4j that the MVP of Aura was done and would they like to come along and try it out. So we got a few people running on these instances that we were managing by hand. And once we had those internal customers, we actually started to build the system. Starting from these first 2 hand-managed EC2 instances, we gradually automated the system, improved the monitoring, adding new features, all the while keeping the system working for our customers. And throughout the time that we've been building Aura and building a team to deliver and operate and support it, we've had this customer-first operational mindset. Because we started operating the system in production before we'd even started writing the code, everything that we've learned about operating Neo4j at scale on cloud infrastructure has been built into the system itself, rather than having to be retrofitted after we learned how to really run it. And of course, as we've been building the system, we've also built a team. There were a couple of us, one part-time, running those first hand-managed EC2 instances. Now there are 30 of us in product engineering alone. And as we've grown that team, it's been constantly focused around the running production system. All the engineers have been involved in keeping the system running, and they see every day what are the effects of the changes that they make on the system and how that affects the experience of our customers. And the evolution of the structure of the team as it's grown has been centered around the running production system itself. As the engineering team grew, obviously we had to introduce some structure into it. And the first structure we introduced was to have a rotating operations sub-team within the delivery team that dealt with all the immediate operational concerns, while the rest of the team could focus on delivery. And that rotating sub-team has naturally evolved into the SRE team that we have today. So for us, introducing SRE as a practice into Neo4j has been a natural consequence of building a team centered around the running production system. The next decision I'm going to talk about is an architectural one. When I showed you the overview of our architecture earlier, I described how the system runs on two separate Kubernetes clusters, one of which we call the brain, that runs the shared elements of the system, such as the console and parts of the control plane and monitoring components. We also have components that run in there that self-test the system, that drive load against the system and ensure that everything is working as expected. And the other Kubernetes cluster, the Orchestra, is where the databases themselves run. We've installed into the Orchestra cluster a kind of Kubernetes plugin called an operator. The operator pattern is one used to extend Kubernetes, both the API and the internals, to manage custom resources as well as the standard built-in ones. And we've written and installed a plugin for managing Neo4j databases specifically. It contains the logic needed to deal with the life cycle of cluster members and other aspects of database operation. I'll talk a bit more later about how we actually run the databases, but the key point now is that an operator is a self-contained unit with an API that runs Neo4j databases. Orchestras are not only self-contained, they're also repeatable. And this is the decision that we made to split the system into a central shared unit, the brain, and an arbitrary number of orchestras that I want to talk about now. Early on in building the system, we took the decision to separate the workload into these two distinct types of Kubernetes cluster, and to ensure that, at least in principle, we could add more orchestras to the system later over time, although to begin with, we had only one. The simplest thing to do would have been just to run the databases inside the same Kubernetes cluster as everything else. Kubernetes provides sufficient workload separation using namespaces, node pools, and networks, so that would have been a reasonable decision. But thinking ahead about how the system might evolve over time, we wanted to give ourselves the opportunity to have the power that an Orchestra abstraction would give us. And we thought we would find any number of possible uses for that abstraction as the system developed, and it turned out that we were right. As a matter of policy, we use Managed Kubernetes Services rather than running Kubernetes ourselves, which is another good decision that we made. That means that we use GKE when we're on Google Cloud, and we use EKS on AWS. So the process of creating a new Orchestra involves using the cloud provider's APIs to summon a Kubernetes cluster into being with appropriately configured node pools, and we install our operator into it and set up one or two other bits of infrastructure that are needed for running the orchestras. To allow us to stamp out orchestras as we need them, we've had to put a lot of work into automating that process. It's quite delicate and often a bit occasionally error prone, but we've put a lot of work into making that reliable and flexible enough for our needs. So what is the Orchestra abstraction used for? One of the reasons we anticipated needing multiple orchestras but have not yet actually had to use it for this is for scale. There's a hard limit on the number of nodes and containers that you can run within a given Kubernetes cluster. What that limit is depends on how the cluster has been set up. But there is always going to be a limit. And even in the medium term, we're a long way away from reaching that limit. It's many thousands of containers, but it's always good to know that you've got an out. And so if we ever do nudge up against that constraint, we know we've got a way of scaling away from it. More practically, there are also limits to the scalability of the components that we've written, in particular the operator, but also other control plane and monitoring components. And that places a hard limit on the number of databases that we're able to run within each of these orchestras. Those limits can be raised by optimization, but the ability to scale our orchestras horizontally means that we don't have to do that optimization work in cases where perhaps the engineering capacity is being used to deal with other priorities. Instead, we can just stamp out another orchestra with very little work. We also use the orchestras to provide support for Neo4j Aura in different geographies. We run orchestras in a number of different cloud provider regions, and our customers can choose which regions they want their databases running in. Adding support for a new region is as simple as creating a new orchestra. And today we've got orchestras running in 15 different cloud provider regions around the world. as well as different regions. As I mentioned before, we support different cloud providers. We've been building on GCP originally, and we've recently launched an EAP of Aura Enterprise on AWS and plan to extend the support to Azure in future. Of course, we use the Orchestra abstraction to make that possible as well. Adding support for a new cloud provider is not just a question of stamping out a new Orchestra. It's a lot more complex than that, but it's made enormously simpler by having this abstraction in place. The orchestras running on AWS are using a different Kubernetes service to those on GCP. As a consequence, we have to configure them differently, add extra bits of infrastructure to bring them up to feature parity with the GKE clusters. But once they're running and have the Neo4j operator installed, they present exactly the same API to the rest of the system, to the brain, as the orchestras that are running on GCP. And so a huge amount of the variation between cloud providers and the complexity implied by that is hidden behind the API in the Orchestra implementation. We've recently launched Aura Enterprise, and one of the features that Aura Enterprise provides is an increased level of workload isolation. Aura Enterprise databases run in a virtual network dedicated to a single enterprise customer. Again, we've been able to implement this fairly simply. We've created a VPC for each customer, and then within that VPC, we stand up individual orchestras for the customer to support the regions that customer needs. Again, this is quite a complex implementation, particularly to do with security and networking. But the surface exposed to the rest of the system is completely uniform with the other orchestras, so that complexity doesn't leak out into the rest of the system. And finally, orchestras make it easy for us to run different types of database. Behind the scenes, most Neo4j Aura database are running as clusters in order to provide high availability. So we run 3 instances of Neo4j collaborating together using our Raft clustering mechanisms. And so that if one of those instances fails because of a problem with the underlying hardware or with the running process, or if we need to make operational changes to replace the instances in the cluster as a whole can continue to run and continue to provide service. And that's how most of our databases run. However, we've just started to make available a free version of Aura, and that runs as single instances for cost reasons. It also runs only one small size of database, whereas in the other databases in the system, the customers are able to choose from a wide range of different sizes. As a result, the infrastructure needs for these free databases are very different from the professional or enterprise databases. And they also, as you would imagine, have very different usage and operational characteristics to the clusters. And so that we can provide a carefully tuned environment for the different types of databases, particularly for cost effectiveness of the free tier, we do that by providing them with their own dedicated orchestra, which can be configured and set up in the way to ensure that the environment is just what they need. We plan to do the same in future for other specialized databases running in Aura, for example, those customized to run graph data science workloads. So this architectural abstraction of the orchestra gives us a huge amount of flexibility and power, enables us to scale in various directions along various feature and size axes, and also to hide all sorts of the complexity that those introduce. From its early simple beginnings, we've extended Aura in a variety of different ways, all while maintaining this architectural uniformity that enormously simplifies many aspects of development and operations. The last decision I'm going to talk about relates to how we manage the Neo4j databases themselves. In particular, how we've designed the system to respond over time, both to the routine load that our users place on the system in creating, resizing, destroying databases, and also responding to the problems that inevitably happen in any distributed system. I described earlier how we started out managing single instances in Aura by hand. And our first implementation of the database management in code took a very imperative approach, what Martin Fowler calls the transaction script pattern. It was more or less a literal translation of the operations that we'd early been carrying out by hand into code. And this worked well up to a point, but as the complexity grew and we looked forward to much larger scale, more complex functionality, the weaknesses began to show. In particular, error handling was difficult, and recovery from failure was also clearly going to be problematic as we tried to handle more complex situations. Every potential error needed to be specially handled, often with complex rollback logic to back out previous steps in the transaction script. And for any particular kind of failure, you needed special case handling in the code to handle that one specific failure. And we expected that those weaknesses to be magnified over time, not only because the scale that we were operating at, but also because we wanted to switch from these single instances to running Neo4j clusters in order to increase the availability of the databases. And of course, operating clusters is inevitably much more complex than operating single instances. So we thought long and hard about this, in particular how to make the system naturally self-healing without lots of special case code. And we came up with what we call the reconciliation model. That is, we have a source of truth, a record in the system, which describes the desired state of the system and how it should look. And then, for example, which databases should be running at any given time. And then we have a process which we call a reconciler, which observes that source of truth and compares it to what actually exists in the system and carries out a reconciliation process by modifying the running resources to match what should exist. And importantly, it only ever tries to make a small, safe step in the direction of the desired state, rather than trying to change the whole state of the system in one big jump. And it's these small steps that are crucial to the robustness of this approach. As let's take a concrete example of the process of creating a database. So a customer comes to the system and they click a button in the console to say that they'd like to have a database created for them. And this is what's happening more or less behind the scenes. So we write a new record, the database, into the system of record. And then the reconciliation process sees that that record exists, and it knows that if that database is running, there must be 3 instances running as a cluster to serve that database. So it looks into what's actually running and it sees that there are no databases, no instances running for that database. And so one at a time, in a series of small steps, it will create those 3 instances. And now let's consider a different case where there is some sort of failure happens in the system. One of the instances in an existing cluster is lost. So here's the cluster operating. One of the instances is lost. The reconciler is going to look at the system of record. It sees that there should be one database that exists. And then it goes and looks at what's actually running. And it sees that instead of 3 instances, there are only 2 running. And so it knows that the next small step it needs to make is to add back the 3rd instance of that cluster. So you can see that these 2 cases, where the first where we're adding the 3rd instance of a new cluster and the second repairing a cluster that's lost one of its instances, are essentially indistinguishable to the reconciler. So having built a system that creates clusters in these small stepwise reconciliation manner, you more or less get self-healing of the cluster in the face of instance failure for free. So instead of an imperative model, we have one that is declarative, convergent, and to a certain extent stateless. Although we have this record of what should exist, we don't need to track the progress of ongoing operations in order to achieve the desired outcome. And that means that all of the error handling can be local to the actual operation that fails. We don't need to worry about any rollback logic. And it also means that the system is naturally self-healing, because any deviation, it can correct any deviation from what ought to exist. Of course, there's a cost here. The design that you end up with here is rather decoupled, with potential attendant problems about reasoning about why things happen. And there's no straight line from a request to its fulfillment, meaning that in some cases, the state of the fulfillment of a request can be hard to track. For example, keeping track of a request to create a database so that we can report progress to a user. There are ways of solving these problems, but they add some cost to the system. So when we first came up with a solution on paper, as a kind of thought experiment, we were pretty happy with it, but it was a very ambitious architectural change, and it required a huge amount of change in the system. And we weren't aware of any other systems that work this way. The kind of orchestration we're doing here, it's very specialized as we're doing it specifically for Neo4j, but these kind of problems have been solved by other systems over time. And we felt that if we had actually come up with a good idea, then someone else should have come up with it too. So we wanted to try and find another system that worked in a similar way to kind of reassure ourselves that we were heading on the right track. We learned quite a lot about Kubernetes by this point, and it occurred to us that the problem was very similar to the problem that Kubernetes solves. And so we thought we'd have a look inside Kubernetes and see how it works internally. So we cracked open the code and had a read and discovered that, to our surprise, this is exactly how Kubernetes works. And it very closely follows the reconciliation model that we proposed. Kubernetes has a rich and rather abstract data model. Containers are aggregated into pods, which are scheduled on nodes and exposed via services. And there are higher level resources which are composed of these in turn. For example, replica sets ensure that there are multiple copies of a given pod running, and then deployments add further sophistication on top of those replica sets, giving fine-grained control of how pod updates are rolled out. These resources are stored in a database, etcd, which acts as the system of record for Kubernetes. And then inside the Kubernetes master, there are a number of controllers running, roughly one for each resource type. There is a node controller, a deployment controller, and so on. And these controllers are the reconcilers of our model, and they follow exactly the reconciliation model that I outlined earlier. For example, the replica set controller examines the replica set resources that are defined in the database, and then it looks to see which pods are present corresponding to those replica sets. It works out which pods are missing or which ones exist but shouldn't, and creates or deletes pod resources as appropriate. It also makes updates to the state recorded in the replica set depending on the state of the underlying pods, which it uses to calculate the effective state of those replica sets, and so on up the stack. And the bonus here is that Kubernetes not only uses this model internally, but it provides an extension mechanism to make it easy for consumers of Kubernetes to do the same. You can define custom resource types called CRDs and deploy custom controllers that run inside Kubernetes itself and manage the resources that are specified in those CRDs. And this is exactly the Kubernetes operator pattern that I mentioned earlier. So we not only have been able to use Kubernetes as a model for our work, we've also then written one of these operators, a Neo4j operator, which we use for managing the Neo4j databases in the system. So with the reassurance of Kubernetes as a model, we were able to make this decision and move from the imperative approach to this more declarative and decoupled one. And we've been very happy with the results. Our database management code has stopped growing in complexity to handle individual failure cases and other special cases. And over time, we've even been able to refactor it towards becoming more simpler and more reliable by introducing a hierarchy of resource types and their controllers of our own, just as Kubernetes has its own hierarchy of resource types. So I've talked through three of the key decisions we made while we were building Neo4j Aura. Of course, the project wasn't a straight run through those decisions. There were plenty of missteps and reconsiderations along the way. But I hope what I've talked about here has given you a useful insight into how Aura works under the hood and how we've gone about building it. And now I'd be very happy to answer any questions that you've got.
Great. Thank you so much, Ben. That was so informative and very insightful. Thank you. And we've had a ton of questions that have come in. And I want to remind the audience that if they do have a question, you can type it into the questions tab located at the top of your screen. And if we don't get to your question during this session, someone on the Neo4j team will reach out to you directly, or you can also send an email to webinar@neo4j.com and we'll get that routed in the right direction. But let's start with the ones that we've gotten so far. So here's one that actually came in a few different ways, but it's basically, what differences did you encounter between GCP's and AWS's Managed Kubernetes Services?
So when we first started building Aura, we were keen to use Kubernetes, and we looked at the available options. We considered running Kubernetes ourselves. We decided that we were definitely not going to try that. Just learning to use Kubernetes was a big enough step. Learning to run it as well would have been a huge amount of effort. So we were looking for managed Kubernetes services. And as I said at the beginning, we were running on AWS using EC2 instances before we used Kubernetes. But looking at what was available, it seemed that at the time, and this was a few years ago, that EKS, AWS's managed Kubernetes service, didn't seem to be ready for us. So instead, we decided to move to GCP and make use of GKE, which was at the time much more fully featured and seemed to be ready for production in a way that EKS wasn't. GKE has been very good to us and very successful. And then recently we've extended support to AWS, and so we've kind of moved back to AWS and have now adopted EKS. And now it seems to be pretty successful. It works fine for us. It is somewhat shorter on features than GCP. There are a couple of things that we've had to implement ourselves, which are available by default on GKE. Auto scaling, we've put a node auto scaler into the system that we run ourselves. And we also have to do log aggregation ourselves. So we run our own daemon sets inside the cluster to aggregate and send logs off to a centralized system, whereas those features both kind of come by default in GKE. The other benefit of GKE is that the GCE instances appear to be a bit more stable than the EC2 instances in our experience. And the live migration, there's some crazy black magic that GCP are able to do to live migrate running servers. That means that you essentially see no failures at all, whereas there are occasional failures on EC2. But since we've implemented on EKS, we haven't had any serious problems. So we're kind of happy with both of them. But GK is a bit more fully featured.
I don't know how you keep track of all those acronyms.
Yeah, I'm sorry about that. I should have something flashing up behind me.
That's okay. We'll have to hand out a little appendix. So here's another question that comes in that's asking about if you could talk more about customer workloads and how they're isolated from each other in Aura Enterprise. Yes. So
as I described, this is one of the kind of main features of Aura Enterprise that we're happy to provide to our enterprise customers, to completely isolate their workloads from those of all the other customers of Neo4j Aura. And the way we do that is we isolate them on GCP within their own project. On AWS within a dedicated account for that customer. And so that provides what the cloud providers, that's the kind of cloud providers recommendation for the very highest level of isolation. And then within the GCP project or the AWS account, we run a VPC. That's a virtual private cloud, which is effectively a private network within the cloud provider's infrastructure. They build a dedicated network just for that one customer, and then all of the workloads run on clusters within those. And so there's no possibility of communication between those customers' clusters and someone else's. We also we store backups in the S3 and Google Cloud Storage buckets and various other bits of storage in the system, and all of those too are located within the projects for the customers, and so they're completely isolated from all the other workloads.
Great, thank you. So speaking of communication, how do components running in the brain communicate with all these different orchestras?
Yeah, so we have we have a lot of orchestras running now in the system. Our production system, it's over 30. I'm not sure exactly what the number is today, and that's so the different regions around the world for our professional product. And then, as I said, each of our enterprise customers gets at least one orchestra of their own, and so we're adding more and more of these every day. That means that we can't afford for the brain to be going and talking to each one of these clusters individually and to go and have to kind of look up the database management system, the console, and so on. Can't look these up. So what we've done is we've built a Kubernetes proxy. So this is a proxy for the Kubernetes API, which does address translation. So we use just ordinary Kubernetes clients within the rest of our code that can know how to talk to the Kubernetes API. We've got Go code, we've got Python code, command line tools, and they just talk natively to the Kubernetes API. But the address we give them to talk to is the address of this proxy, and then the path in the address includes the database, the ID of the database that they're running, and the proxy is able to then route that request to the appropriate orchestra, the appropriate Kubernetes cluster, and so it kind of multiplexes across the Kubernetes APIs of all the clusters that are running behind the scenes in the different orchestras.
Great, thank you for that. So it looks like we're running a little tight on time, but I wanted to ask this question because I think this is an important one to ask. Did it cause any problems running the system in production at the same time that you were building it? So you talked a little bit before about some black voodoo magic or something. So was there magic going on here as well?
It was more work at the time. At the time, it meant that at any time, the developers could be kind of pulled away from what they were working on by sirens going off, by alerts on the running system to deal with customer problems and make sure that our customers' experience was okay, and that was disruptive. Inevitably, that takes pulling people out of the code slows people down. And as I said, we introduced this operations sub-team to somewhat kind of insulate the rest of the team against that, although people were rotating through it, so they still got exposure to that. So there's no question that day to day it took more of our time to do that, but looked at over the long term, it must have been a huge saving. There must be, I don't know what they were because we didn't do it, but there must have been wrong turns that we'd have taken, features that we'd have implemented in ways that simply wouldn't work in production, and problems that we were able to anticipate and work around because of that experience we'd had all along of running the system as we were building it.
Thank you for that explanation and your honesty with it as well. It looks like we are about out of time for your session, so I want to thank you so much for being with us today. This was a great presentation and a peek under the hood, so thank you so much.
Thank you very much.
And for those in our audience, stay tuned. We have another quick clip from our customer PwC Canada, so be sure to enjoy that. Thank you so much.
Hi, I'm Ivan Zazarski. I lead the financial crime practice at PwC in Canada and part of the Global Financial Crime Unit leadership team. In Canada, our practice encompasses cyber, financial crime, and privacy, and we look to solve important and challenging problems for our clients. Part of that it certainly matters in terms of analytics and providing significant managed insights for our clients in order to make them better, provide better decisioning and clarity of where they are in any particular matter. We first thought that graph analytics and graph database would be a great way to go about providing insights in non-obvious relationships and, of course, all the mathematical constructs behind graph theory. Knowing the theory is one thing, but being able to apply it and leverage that is quite another. So being a mathematician, it's one thing to be able to go ahead and say, yes, you know the theory and you know all the algorithms and so on, and then to apply them. But how do you actually distribute that knowledge and provide the access so that non-mathematicians who are subject matter experts, compliance experts, risk managers, and so on, for them to actually have a dialogue with the data? And so in that fashion, Neo4j really offers a very useful platform in not only incorporating all the algorithms around graph theory, but also providing a usability of those particular theories and make them come to life, so that our clients and our practitioners can have that discussion of what are the relationships and patterns that are meaningful, especially in financial crime. We thought that looking at static databases or relational database management systems, are obviously of high value and been out there for years, but looking at graph database compositions and being able to incorporate the vast library of graph algorithms that is within Aura and Neo4j's platform was a primary value. In addition, it also provided us an accelerator. So going to the cloud allows us to go ahead and set circumstances where we drive hypotheses or labs to identify various patterns. There's a real time savings in the identification and setup time that's different than setting up a relational database management system, deploying that, licensing it, and all the rest of those activities where our investigators just want to get their teeth into something and identify whether or not something's going bump in the night. And being able to do that on Aura is really helpful. The second aspect of where we thought Aura was of great value to us is it's enterprise-wide. So it's not like one department comes up with an idea one day, has to go and license something, has to go ahead and deploy it and make sure that they have IT support and everything else, which is time-consuming, costly, and really gets in the way of driving value to the client, because you need it when you need it. You don't need it 3 months from now. So things degrade in value. It's like a shelf life on stale bread. So if the data is there, you should be able to do it when you need it and how you need it, and Aura really drives that paradigm.